Hi, welcome to a special lecture on linear algebra. Special in the sense that this is an extra or optional lecture. We are going to go beyond the usual topics of this class. So this lecture is intended for students who are interested in theoretical engineering or headed toward mathematics degree as a main degree or as a second degree. Or students who are interested in physics or in any kind of a graduate program. So you want to do a bit more than what is typically required in a course. So you try to pick an area for extra study, research, perhaps work with a faculty on a topic or something. This is something for you so that you know what you are interested in, and also to prepare your resume for where you want to apply. So for today we are going to take an extra look at the problem of projection we brought up in the previous lecture and look at some additional questions and topics that hopefully get your attention. When you look at your textbook, you notice that in every chapter there is one or two additional sections, typically titled something like explorations or writing projects or something. It would be nice for you to go take a look at them and see if there's any of them that interest you, and in that case you want to talk to me or any other faculty member. Perhaps we can make a project out of it or do some additional work. Okay, so let's go ahead and get our topic for today started. So we are going to have a lecture on projections, and this is called Lagniappe. That's an expression in New Orleans for an extra a shopkeeper gives you when you go and shop over there. So we are giving you an extra material here, and instead of giving a cookie or something, we are going to give you some mathematics problems. Okay, so you remember last time we talked about projection. The idea is very simple. Sometimes you have a line, so you have a point outside, and projection simply means you drop a perpendicular, and if there's a point P here, then there's a projection of it, perhaps P prime down here. Or in higher dimensions you can have, say, a plane, and again a point P outside, you still drop the same perpendicular, and down here the point that you have, let's call that P prime again. So going back to this issue, of course you can have a vector like what we drew last time, and then we said draw a projection. So this point is right on the line itself, so the projection is going to go from, this is the start of projection, this is the end of it, and this is the original shape itself. Of course you don't have to be resting on the line. You can be outside here and still talk about the projection. That is, you can have perpendiculars drawn from these two endpoints, and then you have a projection of it down here. Same issue on three-dimensional situation. So I can have a line resting on the plane and drop a perpendicular here, and in a similar scenario as before, we have the original and then the projection. And once again you can have your plane, and this point can be on one side of the plane completely, and then you drop a perpendicular from both ends, and same designation, you have shape here and its projection on this plane. Going beyond this thing, you can have any you can have a plane, and you can have any shape at all, and then projected on this plane. For example, the simplest case perhaps, we can have a triangle here, and then you can drop perpendiculars from the endpoints of this, and well, then of course you are going to have another triangle down here, and let's go color it the same way, so you can have the original and then the projection down here. So if this is a triangle T, perhaps you want to call this T prime or something. So all sorts of questions can be asked in terms of, well, what's the relationship between the projection and the original in terms of length or area or anything of that sort. Let's go start by some simple examples, and then I'll be asking you to work on the problem and let me know how far you got on it, and then we can talk about it. Again, it's all on optional basis. So first item to look at, you remember last time we talked about three-dimensional version of Pythagorean theorem. Let's go back to the original Pythagorean theorem itself. So the Pythagorean theorem says if you have a right triangle where sum of the square of these two sides is square of the hypotenuse. Let's look at this thing from a wider perspective or a different perspective. You can think about this similar to the story of the projection. That is, you can think about an object here, and then you're taking the projection of it on the, say, the x-axis here, if you wish. The yellow will be that, and let's go ahead and color the projection on the y-axis as the green one. So Pythagorean theorem says square of the length of the original is equal to the sum of the square of the two projections. Okay, good. In mathematics, one standard thing that you ask is, how far does such an idea go? What other cases that can we look at that are essentially built on this idea, but perhaps more general settings? What do you mean by more general settings? Well, this is in 2-dimension. Standard question that you could ask, how about 3 dimensions? If you're interested in more mathematical issues, so how about 4 dimensions, and so on? Well, 3-dimension is very standard to ask. The question is, how would this idea look like in 3 dimensions? Well, we answered one version of this thing last time, and that was the following. If you draw a rectangle, and we said either of the diagonals of this, for example, this diagonal is the same as, so now we are drawing it this way, that diagonal squared is equal to sum of the square of these two sides of the rectangle. And that is an idea that immediately generalizes to 3 dimensions. So in 3 dimension you have something like this. So we say now we draw a box. So I just go quickly draw a box. You want to practice and draw it better than I do, but let's move ahead. So here I make a box, and then we said if you look at this diagonal, so let's consider this as a diagonal, then it has 3 projections on the 3 axes. So this is projection number 1, and then say this is projection number 2, and say this is projection number 3. So last time we said that square of this blue one is equal to square of the yellow plus square of green plus square of purple. So that was the Pythagorean theorem. So if it was A, B, and C, and this was D, then D squared was equal to A squared plus B squared plus C squared. We saw a proof of that last time, and hopefully you can reproduce that. The question, what else can we extract out of this situation? and what other things can we say. So let me first ask you a couple of questions. So I go back to this box again. Let me draw a box as clearly as I can. Draw it big so that we can label stuff in it easier. That okay, how are we going to do this? Let's so maybe I just okay. I drew the diagonal of this box. Now this diagonal makes angles with a variety of things. Let me go ahead and call this angle, maybe I color it and label it so that's clear. Let's call this angle alpha, and maybe this one angle beta. Yeah, let's see if we can make it clear. This one angle gamma. Tell me, what do you think is cosine square of alpha plus cosine square of beta plus cosine square of gamma? Find out what that thing is. You might want to remember some basic identities in trigonometry. So remember, if I have, like in this case, if I have this one, I call this alpha and call this thing beta. What do you think is cosine square of alpha plus cosine square of beta? Okay, something very familiar from trigonometry you have there. You have something like that here. So try to answer that, figure out what it is, and also come up with a justification, or we call that a proof. Come up with a proof of what you think that is. Another problem almost identical to what we just said, slight variation on the same theme. Again, I draw a box. I draw a better box. So again, I draw this one. Now I ask about different angles. Now this time I draw a diagonal here and ask about this angle. Let's call this thing alpha prime, and I draw another diagonal here and another diagonal here and ask about these. So that one would be, let's call it well, to be symmetric I have to call them a bit different than I did. Let me call this one gamma prime, and let me call this one, what would be that, alpha prime, and then say this one, call it beta prime. Same question, what is cosine square of alpha prime, cosine square of beta prime, cosine square of gamma prime? As soon as you answer that, you can answer this thing very quickly. Just work on it. Let's see how far we get. Okay, next issue up is all the projections that we have been talking about is for a line. How about something more involved than a line? We said next up is having, say, a triangle. If you have a triangle and you project it, well, you get another triangle. You can talk about areas of these two. So if I have this is t and this is t prime, think about the following. How are areas of t and t prime related to each other? So notice I'm not giving you any answers or anything. I'm asking you to think about these things. Any of these topics that catches your fancy, think about it, form an idea, and then if you want to talk to me about it, I'm always available. So well, what do you want to do with this? Well, we started by saying that Pythagorean theorem can be thought about as a projection of one line on those two axes, and then we said if you want to call this thing A and B and C, then the relationship between them, okay, this was the most famous idea in mathematics, Pythagorean theorem, sometimes called bride of all theorems, is that, well, how does that work in 3 dimensions and for shapes like triangles and such? Here, let me bring up a demo for you. So here, this black triangle is the original that is standing in a 3-dimensional space. I'm projecting it on the XY plane parallel to the Z-axis, so it's a blue one. I project it on this this one would be YZ plane. I get the red one, and project it on this one. This will be XZ plane, and I get this green one. The question is, what do you think is the relationship between these areas? Okay, let me turn it around. So you see, this is actually a 3-dimensional construction. So what do we mean by projection here? Like if I look at it from the end of the x-axis, let's see if my hand can move this thing. You see, the black is right on top of the red. That means the red is the projection of the black. If I turn it around this way, now the black is covering the green, means the green is a projection on that plane. And if you look at it from the top, the blue is a projection down there. So those black one is the main, and the 3 other colored ones are the projections. The question is, what is the relationship between these 4 shapes? Can you find out what is the connection between these 4 shapes? For example, there are 4 areas. In fact, the formula we had in the last lecture, the last formula can give you the answer right away. But first I want you to come up with a guess. What do you think it is? And then try to prove that also. So now this drawing is a little bit hard to draw on a picture by hand. Let's do an easier one. Easier one will be similar to this. Similar to this one, we said let's go everything in the corners, so we have fewer loose lines and everything. So here I have a three-dimensional setup. Sorry. So we can make the problem a little bit easier on ourselves by putting this triangle right at this corner. Okay, so this is going to, maybe I'll draw that in black so it looks like the other one. And the projection of it on this 3 coordinate planes, you have one projection down here, that's this projection, and then you have another projection here, so the sides of this pyramid becomes your projections. So if the main one down on the top, you want to call it T, this one will be projection on the XY plane, maybe you want to call it TZ, and then this one projection on the YZ plane, maybe you want to call it TX, and this one projection on XZ plane, maybe you want to call it TY or whatever. The question is, what is the connection? What's the relationship? What is the connection between T, TX, TY, TZ? This will be a special case. In the case that I show you, this will be more general, but the relationship is the same. Okay, in this case our triangle is up in the space, and those are the 3 projections on the 3 coordinate planes. What is the relationship between these 3? You could guess that, of course, well, we are talking about Pythagorean theorem, so must have something to do with what we mentioned there. And but the idea is, well, what is the formula and how do you actually establish it? For the finale of this, remember last time we had the so-called law of cosine. We said law of cosine, instead of looking at this 90-degree angles, it says, well, what if my triangle wasn't 90 degree? Or what if this was A and B and this was theta? And then the question was, what is C in terms of all of these things? And you remember that we had this correction to Pythagorean theorem. It's called a law of cosines. Good for situations where the angle is not 90 degrees. Well, what do you think is would be the idea in 3 dimension? So the question is, what is law of cosines in 3D? What kind of a shape could we be talking about? What are the ingredients of that idea, and how do we establish it? Okay, so I'm leaving the statement of the question to you, and then of course next up would be, how do you actually establish that? So several general ideas. Again, I want to strongly recommend that you read the additional sections in the textbook. They have labels. They're typically in blue, so let me write it in blue. Something called explorations. So in chapter 1 you have explorations in geometry. Some ideas from geometry is being shown here by using vectors. If you want to work on that, let me know. Then there is exploration on other items, writing projects, and so on. Sometimes historical projects are mentioned. As you go down the list of chapters, you see there's a section on global positioning systems, GPS. There's a section on robotics. There's a section on history of eigenanalysis, and so on. Any of them could be of interest. Okay, thank you for listening. Again, remember, this is just an additional lecture. In case you are interested, I'm going to label these things with like lecture 2.x and so on, so that you know it's not in the regular list of lectures. Until our next regular lecture, good luck and God bless.